This is the second clip in the series of input signals for system identification. We have talked about the importance of characterizing spectral property of the inputs, and we have introduced the step function, the sum of sinusoidal. So in this clip, we continue discussing about other inputs. So this one is white noise. So a white noise input, by the definition, is a signal with a zero mean. It's a stochastic or random signal, and its correlation at different times of UT at different time, expectation of UT, US is entirely zero when T is not equal to S. This is a definition of white noise. In the graph, this is some example of the white noise sequence. Okay, you see that, oh, it's very random. It's ups and down, very highly fluctuated. If you just take a look at the sequence at one particular time, in the next step, I mean, it's unlikely that you can predict whether it's gonna go down or go up. Okay, so very random. We know that the autocorrelation theoretically is a delta function, and this is what we plot. Okay, this is the empirical function that I compute on the computer. So I get this sequence and I use the command correlation. I think it's XCore or something in MATLAB. Okay, you should try. So you see that actually this is a small values of autocorrelation when tau is not 0. So this is a very small. And of course, if you plot the spectrum, theoretically, the spectrum should be flat and the values here, the constant is supposed to be the variance of the white noise. Okay, I think I set it to 1 in this example. So in dB, okay, that's the 0 dB. But of course, in the yellow one, this one is empirical values from the computer. So you see that it may be it looks noisy here, but it's regulated around a constant. Okay, white noise. we already see a brief benefit of white noise is that because of the flat spectrum. So if you apply the white noise input to the system, it can stimulate all frequencies mode of the system. Now, let's move to autoregressive moving average sequence. What we have seen from ARMA is just another type of model. But here, when we talk about the input signal, we talk about it in the sense that what if we use ARMA process as the input to stimulate the system? Okay, is it good? I mean, does it have can it stimulate the system in a very sufficiently amount of information? Okay, so what we're gonna do here is explain how to generate ARMA signal. So we let E to be pseudo random sequence similar to white noise in the sense that the autocorrelation function is 0. Okay. Remember this autocorrelation function when you use the time average instead of ensemble average, because this is the signal that you can produce it yourself. If something that you can produce it yourself is deterministic, okay. But we would like to generate it so that it's similar to white noise. Then we use the sequence of E here as the input of UT that has the equation of ARMA process. Please recall that this is called autoregressive part, and when you do the pink term is a sum of the noise the instant time of noise and the past of noises. Okay, so how are we gonna do this? Of course, user just design the coefficient C1 .CP and coefficients DP. So the user design the polynomial terms in autoregressive part and MA part. But how? We know that, of course, different coefficients give you different polynomials. And the root of those polynomials, those two polynomials determine the zero and poles of your autoregressive process. So if you represent it in terms of transfer function, this is your input signal, U, that is actually ARMA process, right? Your E is noise that you try to make it similar to white noise. Okay. You need to make sure that this ARMA process is stable, is stationary. So the roots of these two polynomials lie outside the unit circle. Again, if try not to be confused with the term outside the unit circle, and because that's the way we define the matrix polynomial term. It might be, it is opposite to our control system point of view, because in control system point of view, when we derive the transfer function, we use this, right? Zi minus A inverse B, right? But then the way we define the matrix polynomial, we define it with the lag operator. So you, so the dummy variable is, you know, Z to the minus 1. So so it's kind of so it's the, when you talk about, okay, what if the transfer function is stable, you know that from control system point of view, the pole of your transfer function has to lie inside the unit circle. But it's just the way we express the matrix polynomial here. So we say the root lies outside the unit circle. So try not to be confused. Okay. So different choice of C and D gives you different spectral characteristics. Okay. So here's in these three examples. This is the transfer function of ARMA process. This is, of course, ARMA. You have both autoregressive part and moving average part, but for G3, it contains only moving average part. Okay, what do we see? Again, we can, for autoregressive part, that gives you the locations of pole. For numerator, which is a moving average part, that gives you the zero, the locations. Okay. If I zoom in, okay, the red one is the ARMA process. The yellow one are the noise, which is of course something that is similar to white noise. If you look at the autocorrelation of ARMA signal, okay, if you look, this is G1, G2, and G3, okay. For G1, your autocorrelation gradually decay, okay. Why and how? Try to find the roots of this polynomial. As I said in another video, when we talk about time series model, state space model, we give you a relationship between the pole of the system dynamic matrix and the autocorrelation functions. That we say, okay, autocorrelation function, you know, how it behaves as a function of K. Oh, it depends on A to the K, where A is a matrix in the state space representation. So it depends on the eigenvalue of k. All right. So for time series model like this, ARMA process, of course, your eigenvalue is associated with the pole of the system. So the rate of decay here is actually specified by the roots of this polynomial. For G2, of course, you see the oscillation of the autocorrelation function. Then I want you to again verify and from the roots of G2. Okay, and for G3, um, is MA is moving. It contains a moving average term. Of course, that's a result in the moving average process as well, where that what you see at the autocorrelation function is going to be the tail is off after a certain order of lag. Okay. So you see that only significant sequence here at lag, probably lag 2. Okay, because the MA term has order of 2. And you see different spectrum as well. Okay, so this has a higher power at the low frequency part. For the second one, it has significant power at the mid band, and for G3, it has higher power at the higher frequencies. So this is the these are the results of playing with the ARMA coefficients, so that you get different characteristics of the input. Okay. Okay, we have the last one. This one is going to be long. Okay, I hope that probably let's see, because this is going to be very long, the pseudo random sequence. Okay, let me break the video again